Okay, we're going to go ahead and get started here. So thank you everybody for coming here in person and on WebEx. Today it's my pleasure to welcome Dr. Joao Dorea from the University of Wisconsin-Madison. He's originally from Brazil, where he did his bachelor's at Bahia State University. And then he went on to pursue a master's and PhD in animal science at the University of Sao Paulo. Following that, he worked for 2 years in industry with DSM down in Brazil, and then he went on to pursue a postdoc at the University of Wisconsin-Madison, focusing on data analytics and sensor technology, working very closely with a geneticist there, although he's not a geneticist, that's okay, we'll still take him and claim him. Following that postdoc, he was hired on within the Department of Animal and Dairy Sciences at University of Wisconsin-Madison as the assistant professor in data analytics and precision technology. And today he's going to talk about a little bit about his research. And then for the graduate students here, there will be a lunch just down the hall with him after the seminar.
Thank you very much, Chris.
Thank you. Yeah.
Are you recording on Zoom?
Yes, we are recording, and for those on WebEx, we will also post it later.
Oh, there's a question in the chat.
No, okay, saying yes, you can hear us. Okay, we'll edit that. Take it over.
Thank you. Thank you very much, Chris. Well, thank you very much for the invitation. I'm very, very honored to be here. It's a great pleasure to be here for the first time. It's a beautiful place, a beautiful campus. I'm very excited to meet you all and see old friends. Rodrigo, if you don't know, Rodrigo got the degree. His master's degree was on the same advisor when I was doing my PhD, so we were on the same program back in Brazil. Then Rodrigo came to right. So Rodrigo came to US and I finished my PhD there, and I went to industry, as Chris mentioned, here in Sao Paulo. And then I came to medicine. Made medicine since 2015. Well, so again, thank you very much, and I hope I can change a little bit those titles and explain a little more, so I don't not consider a geneticist, because with hyperpool phenotyping, computer vision, data analytics, and being coming from a lab, from a geneticist in animal science, so people think I'm a geneticist, but my background is an animal physician. So what we're working now is on hyperpool phenotyping, precision phenotyping, phenomics, pretty much how we can collect animal level information precise, frequent, and cheaper way, so we can improve management decisions, and we can also work with geneticists to have more progress on animal breeding programs. Okay. So today we talk about computer vision systems, and this is a branch of artificial intelligence, so how to use cameras to automatically collect data from the environment, from the animal, process that automatically, and then give us the phenotype that we are looking for. Please. Okay, good. So, well, right now, everybody is watching that conversation about data is accumulating at a tremendous rate, and people talking about more and more about data, but in the past, data was accumulating at a tremendous rate. The problem was how that data was accumulated, and was not very efficient the way that we had the data in the past, and how we could process data and be efficient on how to analyze data and get useful information extract from that data. Indeed, we have much more data now, but I think a big change that happened was that change from collecting data in a piece of papers or in a non-efficient way, and now having that data being stored in computers, in our device, and largely in clouds that we personally use, right? I think everyone has OneDrive, Dropbox, Google Drive, and this is only one single piece of what we see in terms of cloud computing for personal use, but that's more organized the way that it is. And there are companies working with our data and monetizing that data. So in the economy, it became that the most valuable resource is no longer oil, but it's data. There is also something interesting in that sentence here, that as a resource being compared to oil, we need to mine that resource, right, to have useful product. So what those companies are doing, not using the raw data. It doesn't matter if they have my name and my age, but they need to connect that information for other sources of information, then extract useful information. So that's what pretty much you need to do with livestock data. It's not only collecting more data, but it's how you can use that data to have optimized farm management decisions or quick improvement in animal breeding improvement. So at the farm, we have a challenge that is collecting that data. That data is coming from different sources. We have data coming from collars now. We always have that data coming from feed analysis, more robotic milking systems, milk analysis in terms of milk spectra. We can get the raw data from those samples now. We have automatic feeders, cameras. We still have data that is notebooks. We have public data. And those data, they have different structure. Some of them are text, some of them are tabular data like Excel spreadsheets, some of them are image. And the question is, okay, I'm super happy that now I have the data. You can access that data easily. You feel good about that, but the problem is how you combine that. That's not a trivial thing. Okay? I'm gonna give an example. If you have what the cow weight, have the feed composition, and if I have an image of that cow, how you link that to? It's not like two columns that you have a cow information on an Excel spreadsheet, and I have, right? So you have two different types of data. So it's not a simple merging these, especially if you increase the scale of the data collection, and now you have millions of images plus millions of image diet composition and how you combine all of those things in the sense that when you need to analyze, you have all that together. Okay. So one of the things that are really driving the speed is not only about collecting data in an organized way, but how you can process data. So if we look here and we compare the iPhone 6, which probably is outdated now, right? I mean, it's I think like 12 or well, if you look at the clock speed of that iPhone, and when I say clock speed, how many instructions the processor can execute per second, that is 32,000 times faster than the Apollo, which is the computer that put someone on the moon, right? So we could perform with that phone that amount, that ends up being faster than the Apollo computer. In terms of memory, that iPhone, it has 1 million times more memory than the Apollo computer. So that's in your hand, and that's all you have to process data. So while somebody use something that's not that fast and put someone out there, we should be able to get some phenotypes, I think. We work more than that. So that's our reaction now. When you have, okay, I have a computer, I have storage, I have the resource I may buy, I can buy this. Now what do we need to do? What are the right questions we need to ask? What the training that the people that will be working with that data need to have, so we can advance it, really, right? In the field of livestock, specifically, considering that we are a little behind crops. Well, the first thing you imagine, okay, what I need to have is some initiatives that will integrate data. I need to pull data from several softwares, and I need to aggregate that. But I just said that it's not simple. So because not simple, for sure we're gonna have groups working and try to solve that problem. So this is a project called Heavy Brain. This is led by Dr. Victor Cabrera, my colleague, the fact in our department. And he put a team of computer scientists engineers to gather data from different softwares at the farm, integrate that data in campus, and then we could analyze that data easily and create analytics out of it, right? Well, this is going very well, it's going fast, and it's a super interesting and multidisciplinary project. But it's still, when we have that data, we still behind the integration that agriculture is performing. We have weather data, crop, water, soil, and we can see even companies like Microsoft developing cloud resource, this is what's called FarmBeats, that you can pretty much draw a polygon in a piece of map, and you can get soil data, weather data from that specific polygon, and then it's automatically integrated, but you don't have anything even close for life. So plants is going fast. In animal, That integration is happening. I showed one initiative. There are several from other universities and private companies trying to lead that integration. But we're still missing a very important information. That is the animal level information. Okay? That component is very difficult to be integrated because to be integrated, you need to monitor this using sensing technology. Otherwise, you're going to have always maybe sparse and noisy data that we have in terms of body weights, average daily gain, milk yield, which are the same data. Sparse, we need more frequent data. I'm not saying that's bad, but we need behavioral data, body composition data. We need to advance the level of the phenotyping that we collect to advance the tools that we're going to develop in terms of animal health, animal welfare. Okay? Well, to do that, we need to use sensors. That's the most obvious path to collect that information. Several sensors we have tested, a lot of those sensors, wearable sensors, camera, infrared spectroscopy, RFID, sound. And what we are doing in the lab right now, mostly is on the camera side, computer vision. And the reason we started doing wearable, started developing a lot of applications for wearable, but we start seeing the power of the imaging data, and I'll show you why we decided to go on the camera and the image analysis, and so this is what we call computer vision system. Look this. We published this paper in Journal of Animal Science. We're predicting grazing and non-grazing using wearable sensor. Accelerometer, so we have X, Y, Z coordinates. So we have the G-force of the accelerometer. And here you can see clearly the path of animal that's grazing, animal that's non-grazing. So you use these and you train an algorithm that will classify a new data point based on that pattern, and then you can tell if the animal is grazing or not, right? That's very useful. It's very interesting, especially for extensive rangeland and non-confined space. We cannot put a camera. Now, if I remove grazing and non-grazing, so if I take out those labels, you see the patterns, you see that is different, but you cannot classify what's going on unless I have the label, I give you the label, grazing and non-grazing, right? However, if I give you the image, you don't need the label, right? You can see the cow is grazing, the cow is not. So first of all, the image, you can label several aspects of the image. You can annotate information without having to collect any information, just look at the image. That's the first aspect of it. The second is, if I want to predict rumination and I didn't collect that information, it doesn't matter if I have the sensor data, the accelerometer, I don't know when the cow was ruminating or not, right? So here's different. So if I have the image, I know the cow is not grazing, but I also know the cow is ruminating. So if I want to train a classify, to analyze that image, the power that I have in that image in terms of information is greater than what I have in that specific sensor. Okay? And then it can go beyond your primary index, right? So for example, in that image, you can count the number of animals. You can probably say that the hosting cows, hosting heifers, that's green, cloud skies, trees in the background. So there's a lot of information, social interaction, distance among them. If you calculate the area, possibly some stocking rate or something like this. So the information that is in that image is much more than we have in a single sensor. And that's the main reason, thinking in the long term, in 10 years, we have millions and millions of images being collected now, and that is being collected in a temporal scale. And with the advance of the algorithms that are being used to analyze those images, we clearly see that in 5-10 years, we're going to leverage the power of the data by working with imaging data. That's the, I hope I have convinced you that the imaging data is somehow interesting. We have different types of data, right? We have RGB images, the regular image, they're having the surveillance camera. We have 3D image, which are depth image. We measure the distance from the camera to the objects in the scene, and that's how we map. We get a 3D map of the object. And you have thermal cameras and many other cameras like multispectral camera, hyperspectral camera. They're not even working. What we will be working more in this presentation, you'll see, and we work in a lab. Those are RGB and depth cameras. That's what we're using. Okay. Well, a lot of times when we talk about analyzing those images, people usually think we sit at the computer and the student will say, oh, this cow is standing, this cow is lying, this cow is standing, it's going to take notes. And in reality, that's not what we do. We do that because we need labels. But what we do is some algorithms will process that information, the image, and do you give a probability value of that object being standing in line, or if there is a cow or not in the image, and depending on the task you use it. So for that, you need to understand that image It's like any other data. Okay. The only difference is instead of having a vector, when you have milk yield or average daily gain, have one column with that specific variable. For a single image, to consider this a data point, you have a matrix. Okay. So that matrix that contains the pixel values that is related to the color of the image. Right? So in this case, here you have this little cat, it's black and white, so it's 1 and 0s, so it's a binary image. When you think about color image, the difference now that instead of one image of size 35 by 25, now color image, you have one image size, that's the dimension of the image, which determines this number of 35 data points by 35 data points. So 5. Now I have 3 channels, so we have 3 matrices, one on top of the other, red, green, and blue, and all that gives you that color image. Right? That's what we do. We analyze 3 matrices, always when you analyze that image. So keep in mind that every time you collect 1 million images, you collect that amount of data, and you need to process that amount. So how we do that? Well, there are several ways you can use image analysis in a more classical way, but what is the state of the art right now, it's working very well, is the use of deep learning. It's an algorithm that will process those images. And those algorithms are very powerful and can perform simple tasks from image classification, pretty much tell if there is a cat in the image or not. You segment the body of the image, identify all the pixels that are related to the animal body. You can also classify an animal based on the shape, or an object based on the shape, with no color information at all. You can detect an object on the image, and locate that object. And can also perform both the segmentation and detection. We call this instance segmentation. Right? And can be used for image synthesis. Right? How to create a body of a cow that never exists, but it's so real that the algorithm cannot detect what's fake, what's real. What we'll be seeing today is around those 3. That's what we're using this. And it's important. I also, mentioning about crops and livestock. Well, we have challenges in both areas, and a lot of challenges. They're the same. Data is huge. It's heterogeneous. The type of image that we're collecting. A lot of those images, if you collect 1 million images, you cannot label all of them. You cannot open 1 million images and draw a polygon, no animal body in that image. And so the data is noisy, is redundant because if you collect image every 5 seconds, the cow's not moving, right? So 5 sequence that you have in terms of image is the same thing with some flies changing off of the image only, right? And some of the data, there is a spatial and time detect, okay? We share all of that challenge in high-dimensional data in livestock and crops. However, there is a specific point I want to make that get livestock very challenging. When you fly a drone and you get a satellite image of a plot in drone, you're simply and it's fixed. You get the coordinate, the drone flies there 1,000 times and get the same image every time you want that to happen, right? And then if you get that image, you calculate the growth, health status, whatever you want to calculate from the image that you acquire. In cows or in cattle, in animals, your simply unit is not fixed in space. So if you have the camera fixed, your units change. You can get an image of that cow here, but if this cow moves, now for the algorithm, this cow is a new cow. Because what the algorithm understands is the pixel value. And so if I get an object, imagine a matrix with that cow, with that position, we have numbers that will be different from matrix because that position, because the pixel value will change. So now when you train an algorithm to perform identification of a cow in feedback, you need to have as much example as possible of cow in different postures. So then when the cow showed up in a different gait, you're able to identify the cow. Okay. So if that's not happening, the cow will show up and you won't be able to detect the cow in feedback. Now, what do you need to do to have that? Well, the answer might simple. Okay, let's increase feature representation, which means let's get cows in different postures. That's possible, 1,000, millions of images of that cow. So let's collect more data. Well, but the problem is when you collect more data, you increase redundancy of the data, which means that in 2 hours, only this calf here changing, not changing a lot. Okay, so you're storing more data, and you're possibly analyzing the data with 0 improvement in your model to generalize the inference. So Question is, how can we collect the right data and not more data? And it may seem simple, it sounds simple, oh, I'm gonna collect more data and then I decide what I'm gonna do. It may be right if you have a small data set, but if you have 40 cameras sending data every day, every second, so this increases cost to maintain and to keep that data. So the question is, how can we understand the feature representation and collect the right data? Here's just a very simple example, just to illustrate what I'm talking about. If I get those 2,000 images that I just showed you, that's very redundant, right? And I only use the pixel value of that image to cluster those images, and I use that criteria to cluster. I get a 5 clusters. And if I randomly get an image out of those clusters, you see that the feature representation is different. That's why you get 5 clusters. Right? If you go to 6, 7, then the image will start getting similar. You can see all animals and all animals standing, all animals close to the grain bucket. And we can clearly see that, for example, cluster 1, you don't have a lot of images that represented in the data set from that specific cluster, which means if, let's say, this cluster is eating, right? So your performance to detect the animal eating will be not very good because it does not have enough example compared to other clusters you may have. So this can maybe determine, orient, guide you to what the image you need to collect if you want to improve performance, so then being more efficient. And that's what we want to do as we increase the data set size. Okay, this will let us do a better job predicting behavior, and that's one thing that we are interested in the dairy side is how can we predict behavior every 5 seconds or every second, and detect general behavior like standing, eating, and drinking with some reasonable accuracy, and then use that time series of standing time, eating time, drinking time to detect disease. And it's obvious that you can detect the behavior, but if you don't have that identification, so then you're dealing with the group, not dealing with the individual, and what we want to do most of the times are related to the individual. So here we identify the animal based on the color and identifying the behavior based on the posture. So the behavior is general, it doesn't matter the calf, but the identification is related to the black and white pattern, the coat color of that animal. So we are able to identify and cross information who drinking or eating or standing over time. And hopefully use this to predict disease or welfare or things that we indeed need those. We can be more specific, okay? We can not look to general behavior like standing, eating, drinking, but we can, I want to study feeding behavior. You know, how much time they spend in the feeding plant, number of visits, intervals, but it's hard to imagine a posture of visits. Visits is not something represented on the animal. I mean, the animal's not, oh, this is a visit, or this is a eating time, right? You're gonna calculate the variables out of the image. So the way that we thought here was, okay, let's identify the animal only if the animal crossed the headlock. But then put the head on the headlock, I'm counting. Now I know the number of visits, and I have the time stamp, and I can compare eating time, for example. So what we did here, we trained algorithm to identify the animal only when the animal is in that position, that posture. So if the animal is here, the animal is considered background for the algorithm, so it's not detecting that at all. And it's pretty much an animal identification process that we have. The animal is coming, 1 visit, 2 visits, 3 visits, and then we count the number of visits. And then we compare the behavior and we validate this in a testing set. Now I have total eating time, number of visits, visit duration, visit interval, and so on, right? Well, that's quite interesting, and you can start thinking about a lot of possibilities if I have this feeding behavior in a so high frequency. Well, I mentioned about redundancy in the data to train the algorithm, but now you also have redundancy in the data to make inference. You don't want to make inference every second if the animal is not changing, right? So that's another evaluation we performed was, okay, if I have this algorithm trained to recognize the animal, do I need to make inference on those images every 5 seconds, every second, every 10 seconds, every minute? So that's what we evaluated here. Okay. And in the testing set, we detect that when we went up from 20 seconds to 30 seconds, of sample interval, and this, I will explain what the sample interval is. This is a video stream, right? So we have 25 frames per second, okay? So I go and sample an image of that video, and 1 second later I sample another image, or 5 seconds later I sample another image, and I make inference. So we double the error prediction for eating time, okay? Total time spent at feedback, when I went from 20 seconds to 30 seconds. And then if you go to 120 seconds, 90 seconds, it means that you are missing a lot of events on those sampling intervals. Okay. So the conclusion is, you don't need to get that image every second to make inference. It will be expensive for you. And we're going to use a lot of computational resource to make that won't get you anywhere better than doing everything. It's much less good. So hopefully, what we will do with that image analysis is what we have done with the sensor, with the color that's predicting rumination activity. And the question probably in your mind is, why, if you have the image, it's so good, why are you not predicting the disease readily when you start with the color? But the reason was the image we developed from scratch, whole pipeline, the whole camera installation. This is a commercial color, so that was much faster for us to implement. So in that collaboration with folks from Brazil, they inoculate the disease, Anaplasmosis, which is a big deal in Brazil, in Latin America, in terms of economic loss. And we have all animals inoculated, and then we measure active rumination of those heifers. And then we start trying to use the time series and predict what is happening in the blood as a critical level to identify the disease. And we could do this with 5 days, 3 days, with accuracy greater than 80% to identify those diseases. So that's what we hope to do with the camera system. It's exactly the goal. So the question that comes always is, okay, how can you automate that? Because we cannot walk in the barn and just hang cameras there and do batch analysis, collect these and come back and do install again. We need something that we run. And if you think about high throughput phenotyping, you think about 5,000 cows, 1,000 beef cattle or a large feed yard. So how can automate things and get that data in campus every day in real time? So we started developing this in our facility, in our dairy farm in Madison. So we have those 3D cameras. We have 4 exits in the milking parlor. We install 1 camera in each exit to have 4 cameras. And that camera is a depth camera. It gives you RGB, which is the color image, give you that grayscale image that is the infrared. And then we have that depth image that can give us the 3D shape of the object, right? So what that camera is doing is pretty much calculating the distance. And the camera can do that with that depth image, can calculate the distance from the camera to the phone. It's calculating every second. If that distance changes, it means that the animal is passing through. So if the animal is passing, then we collect a sequence of images. And then we send that to the cloud, and then we start processing that image. Okay. So the first step, when the image hits the cloud, there is a trigger, and we have already a deep learning training. It's a classification, it's a classifier algorithm that will basically select what is a good image from the bad image. The good image is the image that I have the entire cow in that image. The bad image is everything. It's blurry, cropped. I won't be able to get the cow body out of it. So then we don't use that. Okay. Now, if I have a good image, the second step is call another algorithm that is trained for image segmentation. And these remove the background and only give me the cow body. Now, it's a binary image, and this is called mask. So I can apply a mask on that image, and if I do this, now if I multiply this one in zeros, I get the cow body and the grayscale image without background and the depth image without background. Now I'm able to perform animal identification using the black and white or body condition score, body weight, whatever you want to use with the 3D image. Okay? So you're probably asking, what's the accuracy for individual animals that using that code, that view, top-down view of the black and white pattern of the cow. And it's very good. It's 94% using the color image. Okay, and I don't have a large group of cows. I have 60 cows, but that's pretty much what we have. We hit in each pen there, and we have a classifier per pen. And if you ask me what happens if I go to 200 cows, 300 cows, a large group, well, these will probably decrease because you're gonna have cows that are more similar to, probably two black cows or two white cows or two cows that are very similar. Especially consider they only have a top-down view, which limits. So if the difference in the cow black and white thing is in the side on the side, so I cannot see from the top-down view. Okay? But at the same time, if you want to add more cameras, so it's more work and more computational resource and more everything. So it's kind of trade-off when you increase quality, resolution, number of cameras, you're gonna lose. Okay. Okay, so that is one problem here. Okay. You need to label. To train an classifier like this, you need to get a training set of images. In this case, we got like 13,000 images. Someone gonna look that image, and they're gonna say cow 1, cow 2, cow 3, cow 4, cow 1, cow 2. The guy will label image by image. Then I will train an algorithm. Then when the cow showed up, I'm able to classify the cow. Well, this is not possible in reality because you have millions of images. So I cannot label everything. So how I can increase the algorithm doing a minimal labeling thing? I mean, I don't want to label 13,000, I want to label 2,000. But the performance won't be 94 if I label 2,000 only. 67, 6%, right? But then there are strategies called pseudo-labeling, for example, for something called, what I described here is supervised learning. You're supervising the whole process. You're telling what the cow is, you train the algorithm, right? There is something called semi-supervised learning. You supervise just a little bit, okay? And then you let the algorithm learn by itself. Now, what we're doing here, we're using something called pseudo-labeling. We have some of the data with label, with minimally labeled, few images. We train the algorithm, the performance is pretty bad. Then I make predictions, but I use the probability value super high, like 98%, that I know that the cow is cow 1. And I get that cow 1 in my training set, and I assume that label, predicted label, as a real label, and then I start retraining. Okay? And we try that to see if that really helps. And we try different thresholds, for example, to assume that it's a true cow based on the predicted value. And that will happen. We made a label 2,000 images, okay, not 13,000. The accuracy to identify those cows was 67%. Okay. Now, I didn't use a threshold, but I said, I don't trust. If the probability is 30%, 40%, whatever come out of the prediction, I will assume that's the cow, and I will retrain. Okay, and that's pretty bad because you have a lot of false animals. You say this cow is 32, the cow is 44, and then you're training wrong. Right? Then let's set 9%, 95%, 98%, and let's see, obvious, you don't have as many images with those probability values assigned, the ID for the identification. So you don't increase that 22, but it doesn't matter what wants the right image. So then we go from 2,000 to 12,000 images. So this 10,000 extra image was predicted values, right? And then we retrained, and then we went up from 67 to 70. Okay, it's still not the 94 that is solved, but it shows that if you do that recursively, we can get step by step getting better. That will make that learn by itself with minimal annotated. And I know the difficult people, and maybe sheep people, is asking, okay, I don't have this black-white thing, I have all black, all white, all brown, so that doesn't work for me. Give me something else, okay? So we're exploring using the shape of the animal as a way to identify the animal. And a lot of questions will come out of this, like, what if the animal changes shape? What if the animal grows, right? So how will we deal with it? Well, initially, we have 38 animals, and we identify the animals using the 3D shape. We test different 3D representations. We have things called voxels, point clouds, and actually use the depth image, which somehow represented 3 dimensions of the object. And we have very good accuracy to identify based on the shape. And we also perform a study with growing calves during 6 weeks. It's a short-term trial, but we train the algorithm to recognize the calf based on shape with data from week 1, and we could recognize the animal at week 5 without any data. So even with the accelerated growth, it didn't change biometrics at the point that I cannot identify the animal at week 5. Now, if you ask me what about week 100, we don't know. So that's what we're doing now. We have more long-term data to say, can I identify, if I have an image of that calf, can I identify this in a year, in 2 years, in 3 years? So that's how much of change the image, the algorithm prediction, and how frequent do I need to retrain the algorithm? Well, you can do several things with those 3D images, not only recognize the end, but also predict body condition score. That's part of the automation that we created. There are several papers in the literature showing doing similarly, body condition classification score for cows using cameras. Our algorithm is giving us 71% accuracy. It's pretty much in the average of what is published with dairy cows. So that's not very high. One of the reasons this is still not it's still subjective, right? Because someone is getting the body condition score, so it's a human predicted label and training the algorithm. So all the errors that are related to that body condition score is going into the training process here. So it's not a direct measurement of the condition, the body condition of the cow. Okay. And with that, we have this whole pipeline automated and collecting data every day. Now, what else we can do? Right? We have this 3D image we can predict body condition score, but I just said that I don't like a lot that idea of the body condition score just because it's subjective. Someone is assigned a body condition score, and I'm training the algorithm to recognize someone's body condition score. So what we're going to do is, okay, can extract volume, area, length, geometric measurements of the cow body, and use this to predict the disease directly, no body condition score. Okay? So in that trial, we collect data from 76 hosting cows, 27,000 images from the prepartum, 3 time points, okay? 21, 14, and 7 days before calving. And we use those images. We have much more. That's just a preliminary data. We have more time points, but that's the data that we have initially. So we're using these 3 time points to see if we can detect a subclinical ketosis in the first 15 days after calving. Okay. To do that, we use 2 types of features we call here: biological features and computational features. Biological features, we extract volume, area, mask. We mask all the pixels that are related to the cow body, which is very correlated with the area. And we also use a deep neural network, which is this giant convolutional neural network, as a way to extract features of the cow body. I won't go into details on these. I'll be glad to talk to you about that. This is the computer extracting edges, contours that are important for a specific classification. This case was a body condition score, even though you're not using body condition score. I'm using the features extracted by the algorithm. Okay, and we combine this 1024 for that specific network with these 3 features. So I have 1027 for each time point: 21, 14, 7 days before calving. Okay, now we are feeding those features in 2 different analytical approaches, doing validation, replicating the validation, tuning the hyperparameters, doing all the homework we need to do. And what we find in terms of result is very promising in our opinion, because we are using only 3D image. Our precision value was 0.65, our recall 0.91 with an F1 score of 0.75. So the question, what that means? Right? Well, it means that if I have 100 cows, and I know for sure 40 we have subclinical ketosis after calving, the algorithm is able to recover 36 of the 40 that will get sick, which is this 91%. Well, it's not quite the same. So if you make the math, it's not quite, because I need to round the number, but that is okay. From the 40, I'm sure 36 I will catch before calving. Now I have 65. That's not good enough yet. Okay, and this is a misclassification. I'm saying, okay, those cows will get sick, and someone go to check, but this cows won't get sick. So it's promising in our opinion, because I'm not losing cows that will get sick and not seeing these. I have actual alerts, which is bad, but not bad as losing cows, missing cows. Now, why is that promising again? It's because I'm only using 3 time points. I'm using only 3D image, and we have a lot of information related to those cows that didn't even add yet, related to diet, pattern, calving interval. We have all the behavioral information of those cows in the prepartum, and we have several time points before calving that we're not using yet, just because the data is huge, so the students are still working on that. So that's very interesting. Another thing we're very interested as well is related to behavior, related to feed management. It's Bunk score. And those operations spend a reasonable amount of time every morning driving a truck and assigning a score for the feed bunks and adjusting diet trucks waiting to deliver feed. And you need to be a trained person, so you don't put anyone that's not trained there to do that. And at the end, even though it works very well, it's still subjectivity related to this and label requirement. And you cannot do that 24/7, right? You do in the morning, maybe you do in the middle of the day, maybe you do in the afternoon, but you don't do that frequently. So what I developed at the university, and the university got interested in apply for a patent, was a system that look at the feed bank, look the animals weight on the feed bank, and then we combine that information to generate some alerts. Okay? So we train the classification, the classifier to detect the feed bank's full, if it's empty, or if I have some sort of leak, a little bit of feed, or medium, which is pretty much full. Okay, but full is when it's just finished delivery. And then we have data from cows, data from beef, and then we train that classifier. And we have 4 classifiers, and there is some subjectivity here. Okay, I need to say that. What is clear, it's empty cattle, no cattle on the feed bank line, or full of cattle on the feed bank line pretty much after delivery, or when everybody comes to eat. And then the low cattle and half cattle, we say that the half of the line is still empty, and low cattle have sometimes have 1, 2, 3 animals eating, so that's what we call classified as well. So there is some subjectivity here. Those two for sure are clear what they are. Those two in the middle could be merged, I would say. Okay. So that's the quality of the classification for the full, medium, low, and empty bunks. For the bunk score, and that's for the cattle behavior. And if you see the medium in full, if you look, you see that some of the disclassification related to those two, and the same for the behavior, the medium and low cattle. These were some of the mistakes of the model, just because from the human standpoint, it's not that clear for sure. I'm admitting it. And you use a deep learning network, a very giant network to train that. Another thing we're doing is detecting an object, and the object is the tractor, so we're relating this to the feed delivery, so we know the time that the truck is coming for feed delivery. Okay, so in that specific farm, there is something interesting that happened. Is the time to deliver feed is between 7 and 7:30 a.m. So if you get that object to tell us if that's on time or not, for 2 different days it's on time, but for that specific day it was 30 minutes late, and for that was 2 hours and 20 minutes late. Okay, so if we zoom in that specific day here, and you can see that's kind of wet, it was raining, there was a big rain, and so the algorithm was predicting empty cattle and no cattle on the bunk, empty cattle, low cattle on the bunk, pretty much nothing. Now at some point 922 it was empty cattle, half cattle bunk, so which means I have no feed, but I have cattle weight on the feed bunk line. Okay. Now 952 the truck. So those red flags happen probably several times during the finishing phase, and it's hard to catch for the nutritionist and from the management standpoint because you don't see those things happen, but probably enough to drive some acidosis and healthy issues if you're considering high grain diets, but this is probably happening all the time. There's just no way to measure if you don't have sensors. Well, something very interesting. This is a collaboration with people in Brazil. They collect a very nice data set. We analyze the data here in Madison with Nelore steers and predicting body weight with 3D cameras in this case. So we use an approach with pigs, and it worked very well in beef. So here we didn't use any fancy deep learning algorithm. We use features related to the body of the animal, like area, length, width, height. And so we use these in different analytical approach to predict body weight. Okay. So we have different phases. So we have weaning, stocking phase, beginner feedlot. We have the whole data fitted here. We have some more variation to the stocking phase just because of the how heterogeneous the animal is in that phase. They're kind of growing all around. So when they get here, they're more standard, more homogeneous, and the feedlot work better actually than the two initial phase. So we did do validation on that data. We use cross-validation to do that. And the artificial network performed very well as one of the analytical approaches. And you can see the error prediction percent here was 4%, 5%, 2% for different phases. So it's very promising result. And so we invested more in these to more into growth development of dairy heifers and other animals. So the way that we have set up it's using RFID. So it's much easier for us to trigger the camera when we have RFID system and then get the ID directly rather than try to identify the animal using 3D shape. So just a lot of animals depend to try to do that. So we're not doing this. And we're using the same idea with dairy calves. So we have a USDA grant that we are tracking animal growth development from birth to the end of the first lactation. Right? So we have all the mammary gland development and body growth development, and we try to use those growth curves to predict the performance of the cow in the first lactation. That's what we're trying to do. And we're extracting all those features, and we are very interested to understand, given a nutritional plan, how the animal is growing. It's more in volume, it's more skeletal development, it's more getting more fatty, and how is that growth being distributed. So if you look at the relationship of those features, volume and body weight, and area and body weight, I mean, that's a very good relationship. And so the prediction is really good. It's fairly good. We use different, again, statistical methods, and that is a testing set. The predicted and observed very well correlated. The error prediction, 6.5 kilograms body weight, is not good as the other one, but we have only here 40 calves. And when compared with our work with beef cattle and pigs with 600 animals, 100 animals, so we have much better results here. So we believe that here is just we have a big data set. Well, I mentioned several times that data, that infrastructure generates tons of information, right? And it's a high dimensional data because one camera is generating 80,000 frame images per day. And so in 4 months, you get 9 terabytes and 414 million images, right? So it's not even possible to select specific image. We don't have servers for speed. So if I want to load the image number 200 million, it will take like a day until you get that folder and then get that field. And so that's the reason, right? Because it's not a single data point. So when you think about 400 million data points you may have here, but then when you think about an image, it's a bunch, it's much more data. And then we use cloud computing, distributed computing, for sure use the infrastructure of the university to analyze those large data. Oops. And we also have another facility with 3D cameras. So we just finished installation of those 3D cameras. So we have 25 3D cameras, monitoring groups of 8 of 200 calves. And lastly, because of the data is so big, we also think about a strategy to reduce size. And I mentioned that we use that animal body 3D representation to get volume, to get area, and then use this to predict body weight. So now what we're doing here, we get a vector in the horizontal dimension here and one in the vertical dimension of that 3D image, and we have to calculate these. So now, instead of having a matrix with zeros and some values related to the pixel with the height thing here, I have one vector, the dimension is one signal, 1 by 936, and I'm using this to predict body weight instead of using the whole image, and I want to know if this is enough to carry information about the animal body. So we're using something called autoencoder, and this autoencoder is an unsupervised method, so pretty much you feed this as input, and this algorithm try to reconstruct the same signal, and to do this, you extract the algorithm extract features from that signal, and we can determine the number of features, so we determine here 20. So if you look at the relationship of those 20 features that are used to reconstruct that signal, it's highly correlated with the animal height, animal weight, and body weight, and volume, and so on. So when we use those 20 features to perform a prediction of body weight, we reduce a little bit prediction quality in the testing set from 9.8 to 78 I-squared. 0.88, we reduce a little bit the root mean square prediction from 6.5 to 6.9. Now, it's slightly reduction we see here, but then if you look the side of the data, from 600 kilobytes of a depth image, we went up to 0.21 kilobytes for that 1D signal. And so it's a huge reduction in data size to perform slightly lower. It's very similar to the whole 2D. So this, thinking about large operation, large feed yards, or large dairy cattle operation, that kind of thing should be taught because it's nice prototyping, but scaling up will depend on those type of problems that we need to solve. Well, almost in time, I guess. I think the point I'm trying to prove is that we need those digital technology to advance to collect better phenotypes, frequent data, And that data over time will give us a lot of power because right now we have a lot of batch analysis. If you go in all labs in the animal science departments around the US, people have very good data, but not always data from 10 years, from 15 years, everyday data, right? That you can do more longitudinal analysis or time series analysis. And I think with the technology, we'll be able to get that type of data more frequent. And this will lead us to maybe we're going to be answering old questions that we couldn't answer before. Not about new questions always, but old questions, but now we can answer them. And the users. So animal level, in our opinion, is super important. We're still working on that in terms of research. That's what our lab is doing most in medicine. We need to leverage artificial intelligence system in other fields. There are other industries developing a lot. So sometimes you're going to see people trying to develop from scratch. And there is no need. You're going to waste money and time if you try to do that. So we need to get together with people, computer science engineers, or even other departments, plant, crop. They're doing very cool things, and it for sure can be done. The other question is how you educate the new generation, the grads, how we create course curriculum to teach more of those skills, not necessarily how to implement a computer vision system, but to understand what computer vision system is, what this AI thing was, machine learning, what the tools for data visualization, what the components are using, they're using outside. And there is a lot going on in the industry. I would say much faster than what's going in academia in that topic. So that's something we have a course, we put together a course in medicine, but it's quite challenging because we don't have textbook, you don't have syllabus from anywhere. So we have building and learning at the same time. There are a lot of job positions, more positions are showing up in academia as well. You can see maybe 2 or 3 open now. I think Virginia Tech has one open, Florida just opened one last week, right? Madison hired, Illinois hired, Nebraska hired. So I think this is growing for the academia standpoint as well. And there are a lot of startup companies coming out of those inventions. The digital technology area will you give a lot of IPs and patents. These will come. It's a very fruitful area for that type of product as well. Well, my lab it's a blend that is a freezer minus 80 with tissue from biopsies, and there are electronics, so it's a mess in that regard. I mean, there's a bench. It divides the electronics from the. I don't have wet lab really, but we do have some samples who sometimes the students they come think that I have a dry lab, only computer and data, but I tell them that no, that data comes from someplace, and then they need to go collect some of that data. We have the question that we want to answer, so they go collect. So we have a very nice group, very nice. Those guys are running the business there. And then those are the funding, supporting actual knowledge, supporting my program. Yep, we have this. If you want to follow and see some cool pictures, I try to post. I'm not very good at it, but we're trying to get better in the social media. Yeah, thank you very much. I'll be glad to answer any questions you may have. Or any disagreement too, it would be good if you do disagree with some of these, even better.
I have a question.
Yeah.
Even though so body condition scoring is very subjective, do you think this technology would ever be used to kind of standardize that, standardized body condition scoring with the use of those cameras, so that standardized method of measuring it, or is that kind of not?
Yeah, that's a good question. If you look, I mean, the agreement between evaluators, it's kind of high, I guess, right? Even the guys that have 3 grad students they're evaluating, it's kind of high. Sometimes it's high because they're training using the same piece of paper, the same instructor, right? It's going to be high. There's a bias there. But what I think we try to investigate now is something like this. If I have body condition score of cows, and let's say I use that image, or I have 3D images, and I use the image to predict the disease directly, okay? What we can do in some of those algorithms is extract a map, a graphical map, that we can see where the algorithm is putting weight on the prediction related to the image. So which part of the body we have the weights on. And this can maybe indicate what the algorithm is using to classify, well, let's assume there is a good classification that exists, the disease. So this will teach us, visual inspection, what should be the important, maybe, aspects of that image. The problem is some of those features that are abstract. You cannot really, it's not volume, it's not changing shape, it's something else. And then is the algorithm will put in a heat map in some specific part of the body, but you won't be able to, what is being seen here? I don't see anything here. And that's that level of feature representation that we may not understand. You won't teach us, or leading us to better evaluation or standardization. So, what I think that you have more is we're gonna maybe use more quantitative aspects like geometric forms of measurement that will be volume, area, Fourier transform, things that are mathematically described, and not like, oh, if this hook is a little bit like this and this is a score 3, and then I think it's 3.25. I think we're gonna have maybe switch a little more for something we can quantify really well. And if this is enough to predict what we need, then we go with those more direct measurement than a score. I'm not saying body can score, it's bad. I mean, it's extremely helpful. Use it in there's tons of research on the importance of these. The only question is how can you get better than that?
First part of your talk, you talked a lot about sort of the challenges in animal identification, the amount of images that need to be collected to even train the system. That was to be adopted manually seems like a huge turn off to producers.
Right.
Like, it seems like technologies already exist for marking animals, EID, for example, or GPS collars, right, sorts of things. What is the advantage in, and those can be integrated. So what is the advantage of trying to classify, identify individual animals using the vision systems rather than just integrating that for, clearly there are other important, useful, powerful pieces that you can make using it. Why not just integrate that technologies?
Yeah, that's an excellent question. And there are two ways that we can look to that. One is related to the management and the phenotypes you're collecting, need identification. If you work with computer vision, then having everything integrated in the same hardware, so no need to extra hardware. I agree with you that should be integrated somehow, at least at the beginning, until you get the mature, maybe 10 years, 15 years, able to have one computer vision system to handle the identification or whatever other phenotype you collect. But I think the other very important way to look at the animal identification with the image is secure food supply chain traceability systems in the future, a blockchain, things that there is no way somebody can fraud or change, or you will be able to track back the animal path along the whole thing, because you won't be able to take the head of the animal, or the body of, right? So it's there, we won't get lost or nothing will happen. Initially thinking about this. It's not thinking that it cannot be fraud, because you can synthesize the image, you can reproduce an image of an animal, but it's far. I don't think that that's I think it's easier that you get tagged when you just get lost, because the animal, the management activity or something like this. And at the same point, if you have those systems installed in the supply chain, packing plants or in the farm, if you should think about a food supply chain tracking system, this would probably be the best technology solution to invest, I would say.
Vision system.
Yeah.
So I can imagine sort of somewhere in the future, just that whole classification thing be just artificial intelligence, where it's it's monitoring individual animals and picking up those defining characteristics itself. And maybe there's value in that ultimately. Is that sort of the direction you think this will?
Well, I think combining sensors will always be there. You always have something the cameras are possible to do. What I think, or my thought process in developing all those technologies with cameras is that with the same hardware, you can have multiple phenotypes. You can have multiple animals. And so we can dilute, the investment of the system if I can monitor behavior, growth development, drinking behavior, feed management, using the same thing, right? And so I think the way that it's going, well, if you have more people working in the field, I mean, it's something super long term, but the way that I see it is getting more consolidated into field technology or one technology that can handle multiple things. And so, I can imagine the future. I mean, if the farmer needs to put one single sensor for each specific phenotype, I don't see how this would play because each sensor will sell, oh, if you put that tag, this will improve this. So the guy will say, if you put that tag, this will improve this. So how much improvement, I mean, that will deliver altogether. And so I think some consolidations will happen. But we don't even have like large companies selling computer vision system right now for livestock, right? So that's something super long, but thinking super long, what I'm trying to do in the lab is how can I use the same system to monitor as much as I can? It goes exactly along with the question.
It's not only that, so if you do like a visual identification or even make a decision, okay, which cat is ready to go to the slaughterhouse, for example. So you make that decision as a feedlot manager based on how much they're gonna gain every single day. And then you kill the animal at the end. So if that identification, you can tell, okay, half of my group is ready to go to the feedlot, and you can sort them out and keep the rest in your group, for example. That's one example of that technology. So you can make decisions. So in Brazil, they have like, for example, scales like in front of the water. So you measure the animal every single time they're gonna drink the water, and then make the decision, okay, that animal is ready to go to the slaughterhouse. Instead of sending the whole group, and probably the whole group is not ready to go to the slaughterhouse, so you make a better decision and make more money on that. That's one thing that I think is very
makes the decision.
the computer makes the decision for you when it's time to send them to the slaughterhouse or even to the feedlot, background or something like that.
Yeah, but that goes back to the same problem. I mean, if you have that technology that decides optimal time to go to slaughterhouse, but then you have to have 15 others to decide, feed manning the other, So, and then that's why I think systems that can consolidate several decisions or several phenotypes on the same thing will advance more than others that are super specific, unless it's something that only that thing can manage. But so that's how I see the advance of those technologies.
What are the issues with drift? Predictive.
Sorry?
Have you had any issues with drift? Not something I'm very familiar with. I know that it's an issue like image classification programs that as it's retraining accuracy decreases drift within an algorithm.
Yeah, let me see if I understand. Like you're talking about overfitting. When you learn so much about that specific thing, and then they'll be able to classify it correctly.
So, yeah.
Yeah, no, yeah, absolutely. We need to use a bunch of regularization on those algorithms to penalize if they learn too much. Pretty much that what it does. We penalize, we increase their, or we apply some penalization that way to say you learn too much because that type of algorithm is like a vacuum. Imagine that you have a piece of meat, you have a vacuum that, right? That's frozen, you put it in the freezer, down, it's frozen. Imagine now that you have a way to take out the piece of meat, and then you have only that form of the plastic of the vacuum, right? You're not able to feed any other thing in that particular shape besides the piece of meat that's frozen, right? So it's pretty much that. I mean, you learn so much about that shape of data that if you feed another one, then accuracy will down because it's just overfeeding. And it learns that's easily to happen in that type of algorithm.
Great. Let's thank Dr. Dorea again. Yeah, grad students' lunch is just going to be down the hall for you.
Sorry,
Okay, I'm gonna work on getting the 6 markets today and never got around.